You're listening to DTFHN for May 12th, 2026. I'm your architecturally isolated host, Jack Hacksman. We are your daily tech feed for Hacker News, a website where people argue about rectangles. Today's a day for stubborn builders who look at the laws of physics and say, yeah, but what if we tried anyway? Let's get into it. There's a mass buried in this post that most readers will scroll right past. It's a single architectural decision, catch_unwind. 2 words in Rust that reveal an entire philosophy of software leadership. MatClad. Alex Claude, the creator of Rust Analyzer, is explaining how he designed a compiler tool that serves 2 completely different contributor populations. On one side, brilliant dedicated engineers working on deep compiler internals like the borrow checker. On the other, weekend warriors. People learning Rust who have an hour or two to scratch an itch. These populations have fundamentally different needs, different quality bars, different commitment levels, and the architecture has to serve both. Here's the move. Each feature in Rust Analyzer runs inside a catch_unwind boundary. Every feature operates on an immutable snapshot of the code state. Follow that design decision to its logical extreme. A feature can crash. Actually crash. And the user never sees it. The data can't be poisoned. The crash is isolated. It literally doesn't matter. Now run that forward. What does this mean for contribution? It means the bar for merging a feature PR is happy path works and is tested. That's it. The code can panic on edge cases, and that's fine. Because the architecture was designed from the start to make that fine. A crash doesn't corrupt state. It doesn't take down the server. It just means one feature didn't return a result this time. And here's the beautiful part. That visible crash becomes a signal that attracts the next contributor to fix it. This is engineering craft at its deepest. Not because the code is clever, but because the architecture encodes a social contract. The build system choices matter too. No C dependencies, builds on stable Rust. Test suite runs in seconds. Every one of those decisions is in service of the same goal. Reduce the activation energy for contribution. Make it so a physicist, or a student, or someone on a Saturday afternoon can clone the repo, build it, fix something, and submit a patch. The post makes the Conway's Law point explicitly. Software mirrors the social architecture of whoever builds it. But MatClad did something rare. He inverted it. Instead of letting the organization dictate the architecture, he designed the architecture to shape the community he wanted. Open contribution, isolated failure, low barrier. This is how open source wins, not by having better code review or stricter standards, but by designing systems where imperfect contributions make the whole thing stronger. The tools exist. The knowledge is available. The architecture just has to let people in. Moving on. I've spent enough time inside CI pipelines to know that the scariest bugs aren't the ones that crash your build. They're the ones that pass every check and ship silently. This TanStack compromise is a masterclass in that category. And honestly, the engineering behind the attack deserves a moment of reluctant admiration before we talk about what it means. Here's what happened. An attacker pushed an orphan commit to a fork of TanStack's repo. Not the main repo. A fork. That commit poisoned the GitHub Actions cache, which is scoped per repo, but shared across pull request target runs. When TanStack's own CI ran, it pulled the tainted cache, which injected a post-install script into the published NPM packages. The payload was clever. It exfiltrated environment variables, installed a persistence mechanism as a systemd service on Linux and a launch agent on macOS, and set up what commenters identified as a dead man's switch for GitHub token monitoring. This wasn't a smash and grab. This was infrastructure. Now run this forward. Imagine every popular open source package on NPM with a CI pipeline that touches GitHub Actions caching. The attack surface isn't the code. It's the build system, the YAML, the implicit trust between a repository and its cache scope. One commenter nailed it. The mental model most maintainers have of their CI pipeline is wrong. There's too much YAML, too many implicit scoping rules, and the gap between what you think your pipeline does and what it actually does is where attackers live. The trusted publishing conversation is worth pulling on. Several commenters pointed out that trusted publishing, where NPM tokens are scoped to CI environment, doesn't help when the attacker is already inside your CI. You've moved the trust boundary, but you haven't eliminated it. You've just made it harder to see. And Mistral's NPM package got hit by the same worm, which tells you this wasn't targeted. It was automated, scanning for exploitable cache configurations across the ecosystem. What I find genuinely impressive about TanStack's response is the postmortem itself. Full transparency, detailed timeline, no corporate hedging. This is builder culture at its best. Something breaks, you open the hood and show everyone exactly what failed and why. That's how the ecosystem learns. That's how defenses improve. The real fix here isn't better tokens or stricter scoping. It's reproducible builds. It's hermetic CI. It's treating your build pipeline with the same paranoia you treat production infrastructure. Because that's exactly what it is. The tools exist. The patterns are known. The question is whether the ecosystem adopts them before the next cache poisoning worm finds a bigger target. Moving on. In 1985, Apple sued Digital Research for making Gem look too much like the Macintosh. They won. DRI had to strip the desktop metaphor down, remove the trash can, cripple the file manager, hobble the thing until it no longer threatened Cupertino's claim over the concept of rectangles on a screen. There's a screenshot on this page of DEM Desktop 1.2 in 16-color EGA mode, captured right before the legal axe fell. 6 kilobytes. That's the size of the PNG. 6 kilobytes to preserve the last moment a PC desktop was allowed to be intuitive before a look and feel lawsuit decided that visual metaphors were private property. This collection from typewritten.org is remarkable not for what it shows, but for what it accidentally documents. The Cambrian explosion of graphical interfaces before the market consolidated into 2.5 options. Vision from 1983 running on a Turbo XT clone. Sun Tools on a Sun 2 had the Acorn Archimedes running Arthur, where a red window frame meant unsaved data, not active focus. A genuinely clever bit of UI thinking that simply vanished from the evolutionary record. Xerox Ventura Publisher proving that desktop publishing didn't have to be a Macintosh monopoly. Each of these was somebody's bet on how humans and computers should talk to each other. The comedy. The deadpan slow-building comedy is in the comments. People looking at these screenshots from 1987 and feeling envious. Envious of scroll bars you could actually see. Window borders you could grab. UI elements that announced themselves visually instead of hiding until you hovered in exactly the right pixel. We spent 40 years of interface design arriving at invisible controls and mystery meet navigation. The Acorn Archimedes had a more discoverable UI than most modern web applications. Run the open-closed test on this history. the systems that let anyone build on them, that published their interface guidelines, that shipped with developer tools. Those are the ones that generated the most creative variety. GM got legally kneecapped not because it was bad engineering, but because it proved open interfaces could commoditize a competitive advantage. Apple's lawsuit wasn't about protecting innovation. It was about protecting scarcity. Every one of these screenshots is a 6-kilobyte reminder that the path not taken was often the more interesting one. The tools existed, the ideas were flowing. The bottleneck was never engineering talent. It was legal departments and licensing models deciding which rectangles you were allowed to draw on your own screen. Builder culture built all of this. Intellectual property law decided most of it had to die. The screenshots survived, though. Someone with QIC tape recovery skills and a dedication to preservation made sure of that. Open access to history is how you learn from it. Closed archives just let the same mistakes repeat. We talked earlier about building in the open. Now, boys say, what happens when the room itself gets loud? One commenter put it plainly, the nuts are always the loudest. That's been true forever. What the Stanford data adds is a number. 3%. 3% of users have ever posted content toxic enough that 9 out of 10 people worldwide would flag it. The median guess from survey respondents was somewhere around a quarter to a third. People were off by an order of magnitude. This parallels something George Gerbner documented starting in 1068 with his Cultural Indicators project at the University of Pennsylvania. Gerbner spent decades measuring what he called mean world syndrome. Heavy television viewers systematically overestimated rates of violence, crime, and danger in their communities. Not because they were irrational, because the sample they were drawing from was curated for engagement. Network news and primetime drama over-indexed on conflict for the same reason. Social feeds do. Now, attention is the product. The mechanism here is precise and worth stating clearly. On Twitter, 0.3% of users shared 80% of contested news. 6% produced 73% of political tweets. On TikTok, 25% of users generated 98% of public videos. These are not opinion statistics. They are production statistics. A tiny fraction of accounts generates the overwhelming majority of what everyone else consumes. Algorithmic ranking then amplifies the most reactive subset of that already skewed output. The downstream effects follow logically. The majority perceives itself as outnumbered and self-censors. The prolific minority perceives itself as representative and escalates. Both groups are responding rationally to a false signal. Several commenters flagged the obvious question. If the incentive structure of algorithmic feeds produces this distortion, and the platforms profit from it, what exactly is the proposed fix? The article is optimistic. The commenters are less so. One noted that the money decides how to run the circus. Another pointed out that algorithmic amplification of toxicity is the business model, not a bug in it. This is where open systems matter. Not as ideology, but as engineering. A feed algorithm you can inspect is one you can correct. A feed algorithm behind a proprietary wall is one that corrects you. The protocol-level work happening in decentralized social projects treats timeline construction as something the user should own. That is the architectural difference between a room with a sound system you control and one where the bouncer picks what you hear. 5 stories in, and we're still finding reasons to grin. This next one is pure joy. Pause. An Adblocker that channels John Carpenter. John Carpenter made a movie in 1988 about a drifter who finds a pair of sunglasses that let him see the real messages hidden inside advertisements. Behind every billboard, every magazine spread, every storefront sign. The sane commands: obey, consume, stay asleep. The movie was a satire about consumer capitalism. But the thing about great satire is it ages into documentary. 37 years later, a developer named Adblocker has taken that premise and turned it into a browser extension. It's a fork of uBlock Origin Lite, itself an open-source ad blocker. And instead of simply hiding ads, it replaces them with white tiles bearing those same slogans. Obey, submit, conform. No independent thought. Every blocked ad gets one phrase picked at random. The technical implementation is worth pulling apart because it reveals something about how the modern web actually works. Adblocker Origin Lite's cosmetic filtering normally injects CSS that sets display to none on ad elements. The digital equivalent of throwing a blanket over something ugly, this fork patches those injection points to instead apply a white overlay with a pseudo-element that reads its content from a custom data attribute. A mutation observer watches for late-loaded ads, because of course, ads load late because the ad tech stack is itself a parasite that attaches after the host page renders. Every new ad element gets tagged with a random carpenter phrase. This is a project built on open source, for King open source, extending open source. The idea sat in a blog post for 10 years before someone built it, because that's how the open ecosystem works. Ideas are seeds, and the soil is public. The code is GPL 3.0, same as upstream. Anyone can take this further. One commenter suggested using a local language model to generate contextual slogans based on what the ad was actually selling. That's the kind of idea that only emerges when the blueprints are accessible. But step back from the implementation and look at what this project actually does. It makes the invisible visible. Every website you visit is saturated with demands on your attention, your wallet, your identity. The ads disappear so seamlessly into design that you stop noticing them. This extension puts the subtext back. It doesn't block the shape of the ad. It fills that shape with honesty. The tools exist. The code is open. Fork it. We talked earlier about AI models writing code for other AI models. So here's the logical next question. $20. That's what it costs to build a production C compiler in Rust. Well, 20,000, but the point stands. Nicholas Carlini pointed 16 Claude agents at the problem, and they wrote 100,000 lines of Rust that boots Linux, compiles PostgreSQL, and runs Doom. A C compiler used to be a graduate thesis. Now it's a weekend with a credit card. The article asks a question that sounds provocative but is actually just obvious once you hear it. If AI writes your code, why are you still picking languages based on what's easy for humans? Python won the last decade because it was fast to learn, fast to ship, and the ecosystem solved 90% of your problem before you wrote line 1. The trade-off was always performance. You shipped a slow version, promised yourself you'd rewrite it in something faster, and never did. Nobody did. That was fine because your competitors didn't either. But here's the first principles problem. Python's advantage was never Python. It was reducing the cost of human cognition. The language is basically executable pseudocode. Easy to read, easy to write, easy to hire for. Every one of those advantages is a human advantage, and the humans aren't writing the code anymore. Strip away the marketing and look at what actually constrains an AI agent. It's the feedback loop. How fast can it write, compile, check, and correct? Rust's compiler is legendarily strict, which made it legendarily hard for humans. But for an agent, every compiler error is a free training signal. The type system isn't a wall. It's a GPS. The language that punished human impatience turns out to reward machine persistence. The evidence is piling up fast. Microsoft rewrote the TypeScript compiler in Go. 10x faster! Andreas Clean ported a JavaScript engine from C++ to Rust in 2 weeks. Steve Klavnik built an entire programming language in 14 days, all of it AI-assisted, all of it in languages that would have taken months by hand. One commenter nailed it. If you've written Python for 10 years, you can smell when the agent is about to shoot itself in the foot. That expertise doesn't evaporate, but the calculus has shifted. The question isn't which language you can write fastest. It's which language runs fastest when the writing is free. The compiler doesn't care about your feelings. Turns out, that's exactly what makes it perfect for machines. Now, machines writing code is one thing, but the best tech still brings humans together. Let me be honest about the strongest case against Rtwatch. You don't need it. Sync play tools already exist. SciTube, Sync Play, WatchTogether. They all coordinate playback across browsers. Some of them scale to dozens of viewers on half a gig of RAM. One commenter even pointed this out, running SciTube with Nginx on a dirt-cheap VPS for 20 people. So why does Rtwatch matter? Here's the question nobody's asking. Who actually has the video? In every existing sync solution, the video file gets sent to each viewer's browser. The client downloads the stream, buffers it locally, and your JavaScript tries to keep everyone's playback position aligned. It works, but the architecture means every viewer has a copy. They can cache it, rip it, scrub ahead. The synchronization is a gentleman's agreement enforced in client-side code. Rtwatch inverts the entire model. The backend decodes a video with GStreamer, and PM WebRTC sends only the current frame. Audio and video. To each connected viewer, the client never touches the file. There is no local buffer to scrub through. When someone pauses, the server stops sending frames. Everyone stops. When someone seeks, the server decodes from the new position. Everyone jumps together. The state lives on the server. Period. Now appreciate the engineering for a moment. Fine is a pure co-implementation of WebRTC. No C bindings, no lib-wide interlevered cloud dependency. No Google's massive native stack. Just Go. They pipe GStreamer's decoding pipeline into WebRTC's media channels. Which means any format GStreamer can eat, and the streamer eats everything. Becomes a synchronized real-time stream. You can even hand it a URL, and it'll pull from the Internet Archive directly. The whole thing builds with Go Build, runs on localhost port 8080, and the web interface is a play button and a seek bar. That's it. Open source, MIT licensed. Maybe 200 lines of Go that actually matter. Someone could fork this tonight and build a private screening room, a watch party platform, a synchronized training video system for a classroom. This is what I love about the Pione project. WebRTC was designed by browser vendors for browser vendors. Pione pulled it out of the browser and put it in the hands of anyone who can write Go. The protocol is open, the implementation is open. And now the use cases are open too, because 1,000 developers can look at Rtwatch and see 1,000 different things to build. The tools exist. The code is right there. We talked earlier about systems that heal themselves. Pause, turns out, brains might join that list. Story 8. What does it mean to put a brain back together? Not metaphorically. Literally. What happens when you find the wiring diagram for how rehabilitation actually works? And then you build a molecule that follows the same blueprint. That's what the UCLA team just did. They started with a question nobody had cleanly answered. What is physical rehab actually doing inside the brain after a stroke? Not the hand-wavy version, the circuit-level mechanism. And they found it. Stroke doesn't just kill neurons at the damage site. It disconnects neurons far away from the injury. Specifically, it knocks out a type of cell called a parvalbumin neuron, which generates gamma oscillations. These rhythmic patterns that synchronize distant brain regions so they can coordinate movement. Stroke silences those rhythms. Rehab, when it works, brings them back. The elegance here deserves specificity. They didn't just identify the mechanism. They reverse-engineered it into a drug target. DDL920 excites parvalbumin neurons directly, regenerating gamma oscillations chemically. In mice, it produced significant recovery in movement control, a molecule doing the work of months of physical therapy. Pull this thread and you land somewhere remarkable. Stroke is the leading cause of adult disability. Most patients can't sustain the rehab intensity needed for meaningful recovery. The physical demands are brutal. The results are modest. And the whole field has been stuck in a pre-molecular era while cardiology and oncology moved on to targeted therapeutics decades ago. This drug doesn't just treat symptoms. It reproduces the mechanism of recovery itself. One commenter asked the obvious question. Does this work for Alzheimer's? Others pointed to psychedelics opening critical periods for neural rewiring. The parvalbumin pathway might be a common thread running through neuroplasticity research that nobody had isolated cleanly until now. This is still in mice. Safety and efficacy studies are ahead. But the discovery underneath, that rehabilitation has a molecular signature, and that signature can be synthesized. That changes the entire framework for neurological recovery. The brain isn't a black box. It's a circuit, and circuits can be repaired. The paper is in Nature Communications. The compound is public. The mechanism is published. Anyone with a lab can build on this tonight. We talked earlier about infrastructure choices mattering. Well, here's a big one. Story 9, Claude Platform on AWS. Buried in paragraph 3 of the announcement is one of those phrases that reads like legal boilerplate, but is actually the entire business model. Fully retires against existing commitments. 7 words. That's the product. Everything else is packaging. Here's what that means in practice. Enterprise customers sign massive AWS commitment deals. Spend X million over 3 years. Get a discount. Then they have to burn through that commitment or lose it. Anthropic just made Claude a valid line item on that burn down. Your company already owes AWS the money. Now you can spend it on AI agents instead of more Lambda invocations. Nobody asked for. Let me play devil's advocate for a moment, because the strongest case for this arrangement is real. IAM authentication means no new credential management. CloudTrail means your security team doesn't need a separate audit pipeline. One invoice, one vendor relationship. For a CISO at a Fortune 500, this is genuinely less attack surface. Fewer compliance conversations, fewer procurement headaches. That's not nothing. But run this forward. You're an engineering team that picked Claude because the model was good. Your billing now flows through AWS commitments. Your auth is IAM. Your audit trail is CloudTrail. Your agents run on AWS infrastructure. One of the comments nailed it. A startup on AWS credits saying the more we can proxy through AWS, the better. That's the gravity well working exactly as designed. The model becomes a line item on someone else's ledger. Anthropic ships features same day to this platform, which is genuinely unusual for a cloud marketplace integration. Bedrock customers have historically waited, but the architecture tells you who operates what. Anthropic runs the service. Data processed outside the AWS boundary. It's Claude wearing an AWS badge. The question someone in the comments asked about EU inference. That silence is loud. The comedy here is structural. Every cloud platform's playbook is identical. Make it easy to start. Make it expensive to leave. Anthropic gets distribution. AWS gets commitment retirement. The customer gets convenience now and a migration problem later. The tools are good. The lock-in is the product. Remember that radio telescope we talked about earlier? Same energy. Let's go even deeper into the spectrum. Story 10. Extremely low frequencies. I've spent enough time debugging signal propagation issues to know that when physics says no, you don't argue. You engineer around it. The history of submarine communications is essentially a century-long argument with Maxwell's equations, and Maxwell keeps winning. The problem is elegant in its simplicity. Seawater is conductive. Radio waves die in it. Higher frequencies die faster. The Navy figured this out by 1909, when they bolted brass plates to the hull of the narwhal and tried to conduct signals through the ocean itself. It worked to a depth of 2 feet. 2 feet. They tried floating antenna buoys, trailing wire antennas, every scheme to sneak a conductor to the surface without revealing the submarine's position. Each solution degraded the one thing submarines exist to provide: invisibility. Follow the physics to its logical conclusion. If higher frequencies penetrate less, then lower frequencies penetrate more. How low do you need to go? Extremely low. We're talking 3 to 30 hertz. At those frequencies, a single wavelength stretches across the Earth. The antenna required to transmit at 76 hertz. The frequency the Navy settled on is measured in miles. The transmitter facility at Cutler, Maine, used an array of cables strung between 26 towers across a 2,000-acre site, and that was considered the practical version. The receive side is stranger still. A submarine trailing a long wire antenna at operational depth can detect these signals, but the bandwidth is nearly zero. Transmitting a single 3-letter code group takes 15 minutes. You cannot have a conversation over ELF. You can barely have a notification. The entire system exists to send one message. Come to Periscope Depth and check your mail. A global network of enormous antennas consuming megawatts of power, engineered to tolerances that would impress aerospace, all to transmit a few characters per hour to a wire trailing behind a steel tube in the dark. That is what it looks like when you refuse to accept the physics and build the solution anyway. This has been your daily tech feed for Hacker News for May 12, 2026. This podcast is entirely AI-generated. Scripts by Claude Opus 4.6. Voiced by Quen3TTS. Not affiliated with Hacker News or Y Combinator. Now go build something that makes you grin. We'll see you back here tomorrow.